All right, welcome everyone, both attending in person and online. It is our pleasure to introduce Teresa Huang from Johns Hopkins, and she will be telling us about rethinking symmetries in graph neural networks.
Thank you, Nate. And thanks for the kind invitation. It's my pleasure to be in Columbus for the second time in my life. It's very cold, so thanks for everyone who showed up in person, raising the wind. Okay, so hopefully this talk will be interesting enough. So today I'm going to talk about graph neural network. In particular, I'm going to sort of give you some theoretical insight via the lens of symmetries and rethinking the symmetries that we implement in these networks. So let's get started.
Sorry to interrupt. So I can just minimize this window so that it won't block the view. Yeah, it won't block people online though. So it's just blocking the people in the room.
Okay.
All right.
Okay.
Good.
Cool. So today I'll be talking about graphs. I'll be talking about machine learning. So first of all, I believe we all agree that graphs are ubiquitous objects throughout natural and social sciences. So we see all kinds of graph data happening everywhere, right? We have, and even some very sort of special type of data, say like an audio signal, we can think of it as, a sequence, and which can be thought of as a special type of graph, or even for images, you can think of them as signals instantiated on some regular grid. And this regular grid can be also viewed as a special type of graph. And there are also other kinds of objects like molecules or traffic networks, etc. So graphs are certainly important objects. But then their universality also posed some sort of additional challenges, especially when we wanted to sort of use machine learning to tackle problems or learning problems on graph. In particular, graphs are typically non-Euclidean. So lots of the classical machine learning toolboxes have been developed particularly for Euclidean type of data. But then how do we sort of, perform learning and machine learning algorithm on these type of non-Euclidean data set? And what are the constraints or principles that should be enforced in these kind of data? So that's the problem of graph machine learning. And one canonical approach to deal with learning on these type of non-Euclidean objects is the idea of graph representation learning, also known as graph embedding. So the idea is the following. We have, this graph typically represented as a bunch of vertex and edges. And then we have this adjacency matrix A describing the connectivity of the graph. So each entry Aij describes what's the connectivity or the edge weights between the nodes I and J. So the idea of graph embedding or graph representation learning is, say, I'm going to learn a map H that map the objects in the graph, for example, the node I or node J, to some nice embedding space. And let's call these xi hat or xj hat. And typically, actually for the rest of my talk, I'll be focused on just a Euclidean embedding space. And so the nice thing about this approach is that once I turn this non-Euclidean object, this graph, into these Euclidean embedding vectors, I can plug in my standard Euclidean machine learning toolboxes and perform subsequent inference tasks. For example, node classification, link prediction, etc. But just a minor note, so it is typical that people choose a Euclidean embedding space, but it's not necessary. And for example, in the literature, there are interesting works where people choose, say, non-Euclidean embedding space, for example, hyperbolic space, and try to embed the graph. And there are maybe look for some other additional sort of property of the space. For example, they choose hyperbolic space for hierarchical interpretability of the embedding, etc. But for the rest of my talk, I'm just gonna assume we're dealing with Euclidean embedding space, right? So the idea again is to map these non-Euclidean objects into Euclidean representation, and that's why we call them representation learning. And once you've done that, you can just plug in your conventional Euclidean ML toolboxes to perform the inference task. So that's all nice. And you might ask, okay, what are the maps that we are going to parameterize? So I told you about we're going to learn this map H that map the graph, objects in the graph to Euclidean space. What is H? So in my talk, I'm going to focus graph neural networks as a function class to parameterize H. So let's just set up the notation and make sure everyone's on the same page. So here I denote this graph G with its adjacency matrix representation A. That's a n by n symmetric matrix. And then we're also going to have some no input feature that I'm going to denote as X. And for simplicity, yes, question.
You write n means a fixed parameter n or a, or I simply say that it's a square matrix?
Great question. So for now, when I write n can be any number. So when I think about graphs, I can think about graphs with varying sizes, different graphs. But then later on in my talk, I will talk about some special cases where we consider, for example, n is treated as fixed. But that's a great question. So for now, you can view n as any. And now I'm going to assume that we have some input features, which has n rows. And I'm now just going to treat the input feature dimension as 1 for simplicity. But in fact, it can generalize to k dimension. That's all fine. And with that, I'm able to define what a graph neural network, this object, should look like. So as a neural network, its structure is very similar to any type of neural network. So it consists of a bunch of layers, right? So at each layer, how it does the layer-wise update is given as the following. So the layer output is composed of a graph convolution. That's everything happening within this bracket, and a pointwise nonlinearity. Okay, so you might ask, okay, how does this graph convolution work? Let me give you a pictorial explanation. So let's understand, for example, if we're standing at this red node. So right now we're going to do this operation of A multiply X. So A is the graph adjacency matrix, and X is the vector of all the node features. So when I do A multiply X, if I stand on this node, say node 1 itself, what this operation effectively gives me is to aggregate the node signals or information from my one hop neighbor. So here I'm assuming I have a binary adjacency matrix, and then when I do this, A multiplied by X, I'm effectively just summing, the neighborhood features. And now when I say perform a multiplication with A squared, I'm effectively aggregating information from my 2-hop neighborhood, etc. So with A to the power K, I can aggregate information from my K-hop neighborhood. So I loosely call this thing graph convolution because it has some similarity of the standard convolution on, say, the 2D Euclidean grid, where you're basically trying to take a local patch and aggregate signals in this local patch. So why graph convolution is nice, or why people kind of like parameterize this graph neural network in this way, is because this convolution operation is local in nature. So you can sort of perform these updates in a very efficient manner. And you can even consider some sort of like distributed training. So that makes this thing very lightweight and efficient to compute. But this sort of also kind of hinted that there might be some limitations due to the local nature of the algorithm, which I'll explain in more details later. And so, cool. So I defined two sort of what a typical GNN architecture should look like. So at each layer, it consists with these graph convolution followed by pointwise nonlinearity, and we're going to stack, say, L layers together. That forms a neural network. So you might ask, okay, cool. But what are the sort of interesting research questions in this literature? So I guess the first very important question, especially for like practitioner, is nowadays we see really large scale graph in applications, for example, social networks, etc., that have up to billions of nodes. So how you can scale this type of algorithm in really large graph, well, with guaranteed performance, that's certainly a very, very important question. But perhaps most of my research is trying to say, in order to address this scalability, efficiency type of questions that is very crucial for practical application, we need to have a better theoretical understanding of the properties of these graph neural networks. So in particular, in my research, I focus on these two lines of theoretical question. The first one concerns how expressive are these function class on expressing functions on graph. And I will elaborate to what are the interesting function class on graph and how expressive are these networks. And the second line of the question is, okay, consider like once we train this network, we're gonna deploy it on some unseen test data. So even if I get 0 training loss, can I trust this network will generalize well to the unseen test data set? So this is in standard learning theory, this sort of questions are related to the generalization property of an algorithm. And there's lots of like literature in the generalization for neural networks. In particular, in my talk, I will be giving you some flavor of how we can sort of understanding and generalization of graph neural network from the perspective of symmetry, which, so now here, let me give you sort of a quick roadmap of the next 40 minutes of my talk. So I explained briefly to you what GNN, graph neural networks, are. And I told you that my idea here is to try to have a better theoretical understanding of them. And I'm going to do so use the lens of symmetry. And so in the rest of my talk, I'm going to first try to explain to you how we can understand the expressivity power, expressivity of GNN via the idea of permutation symmetry, that it's sort of enforced by design. And then I'm gonna go on to some specific learning setting where we can sort of answer the generalization question by thinking about different kinds of symmetries that we can induce on a graph. But note that in this setting, actually related to the earlier question, in this setting, I'm gonna focus on a special case where the graph is given fixed. So n is fixed in this setting, but I will remind you and elaborate in more details when we get there. And lastly, I'm going to conclude my talk by sort of throwing out some ongoing research direction that I'm currently actively thinking, which had to do with the notion of probabilistic symmetry. And because this is connected to the idea of nowadays, a lot of these current model machine learning methods have been deployed to generative tasks. Like how do you generate new graph? So in order to do that, you basically have to learn a distribution on graph. And then the sort of the related notion of symmetry will be a probabilistic notion. So I will finish my talk on that, and we can discuss any questions that you might have. And also in my talk, if you have any questions and you want clarification, please feel free to interrupt me. Okay, cool. So let's start with this notion of permutation symmetry. And let's look at this sort of the figure that I give you to illustrate the idea of graph embedding. So you might notice that one sort of key property of a graph is that when we label or order the nodes in a graph, we try to pick an arbitrary choice of the ordering of the nodes, but the choice is arbitrary, right? So when I change the ordering of the nodes, the graph itself remains the same object. So this type of sort of choice or symmetry, it's known as permutation symmetry or permutation invariance. And so therefore, any function or any map, and here this map specifically H, that we wanted to learn on this graph, we want it to be permutation equivariant. So more concretely, if I wanted to write it as a definition, and oh, sorry, here I denote the map as F. But let's say my F takes in the input as the graph adjacency matrix A and some node feature X. And now I can have some permutation action on both the adjacency, which will be permutation by the rows and the columns together, and also the permutation of the node feature, which will be swapping the rows of X. So when I perform this permutation in the input to the map F, I want its output to be permuted accordingly. And I want this to hold for all permutation in the symmetry group of Sn. N is the number of nodes. And I also want it to hold for arbitrary n, because I want this graph neural network to deal with graph with different sizes, right? So effectively, this sort of actually enforce a lot of constraint on the function class that I can choose, because I need to find a function class that satisfy this permutation equivariance. By viewing the neural network itself as a function class.
But would you select?
I select a class. Okay, so I optimize. Yes.
Actually, I'm more precise.
Yes.
You showed us that formula for the C deltas.
Yes. Yeah.
So what do you select?
Okay, so in that, I already picked the function class. Yeah, so that's a function. Like that's a choice of the function class that I already handed to you. Yeah, and I told you that's the standard or most popular formulation of GNN that being used in practice. But there are many different variants, and then I can have a different ways of, say, composing A with the input X, and that could potentially give you another function class. But then the constraint is no matter what kinds of choice you make, you want this function class to be permutation equivariant.
And in that function class, you show that it's usually the variable.
Yes. Yeah. If you, yeah, I think we will all agree to that. But if you want, I'm happy to. Yeah. Yeah. But yeah, that's, yeah. So let me clarify. That's the definition I gave you. That's one choice of the function class, and that's used most popular. But you can have different variants. But then the underlying principle, if you wanted to apply that function class to deal with different graphs, we wanted to satisfy the permutation symmetry as a constraint.
Sorry, say that.
If you wanted to deal with graphs with different sizes, with arbitrary ordering, without matched without matching a priori across different graphs, you want the function class to satisfy permutation symmetry.
Why?
So because for each of the graph, so now, okay, if you look at this function f, it takes the graph A as an input. So now when I label or choose the ordering of the nodes in my input, I make the choice arbitrary.
Sure.
So if I just make another choice, I will hope that the output of my function will sort of be permuted in a compatible way. And that's why I wanted to ensure the permutation invariance.
Sorry, my point is philosophical. You said that if you want to operate with graphs of different sizes and different graphs, then you want to have this variant, right?
Yeah, yeah.
But when I asked that question, you answered something different. Your answer was different from my question than the answer to my question.
I
So
see.
My question, really philosophically, why do you want to have equivariance?
Yeah.
Given that as a design,
Yeah.
as a desideratum, right, like you're saying,
Yeah.
you want to be able to cope with graphs
With different
nature and
sizes.
different sizes.
Yes.
So how does equivariance interact with the different sizes?
I see. So you're saying, okay, yeah. So, okay, different sizes, right? So, the fundamental thing is like the different choice of the orderings of the nodes in a graph, right? So that can be independent with the size of the graph, right? I agree. Okay, cool. Yeah. So, all right. So where we were was sort of this. Okay, I just explained to you. We want any GNN to satisfy this permutation symmetry as a design choice. So now my first question that I had like explained to you earlier is we want to understand how expressive or how powerful our graph neural network to express functions that are permutation equivariant. So how do people do it in this literature? The typical way to answer this question of how powerful are GNN to express permutation equivariant function is by comparing it with sort of established graph invariant, meaning sort of functions that are invariant with the permutation action on graph, or some sort of functions that can be equivariant with respect to the actions of permutation. So here I will give you a bunch of examples, but there are many more out there. So one of the sort of the related function that people have compared GNN with is the idea of eigenvectors, and also known as like spectral embedding in the literature or the community of random graphs or spectral clustering. And so the idea is the following. So here I show you a figure of this very well-known random graph model called stochastic block model, where it's basically, you can think of it as sort of a two cluster graph. And now with this stochastic block model, you basically define what is the edge connectivity within the block and across the block. And having this model, you can sort of sample from this statistical model to generate random graph. And people have used that to model sort of like actual graphs in the real world. And so it's well known that in the statistical network community, if you wanted to say do community detection, meaning that you wanted to say find a cluster of where this node belongs to, you can solve this by using the top k eigenvector for a k-block SVM. And so sort of the community information are encoded in the structure of the eigenvectors. And so that's why a lot of times people have used GNN for tasks related or similar to community detection, for example, like node classification. And that's why there are some works where people try to compare whether GNN can sufficiently express eigenvectors of a graph. Although there are some assumptions need to be made. For example, we need to assume that the graph has simple eigenvalue, because otherwise there is some ambiguity. When we have repeated eigenvalues, there's some ambiguity of rotating the eigenspaces, etc. But I'm just going to give you some brief overview of what kind of different class of invariant and equivariant functions people have looked into. But if you have more questions or interested to know more about it, I can give you more detailed explanations. So another kind of very interesting class of equivariant function people have looked into is this notion of equivariant graph polynomial. And this emerged as like a pretty recent work where basically people are trying to understand how expressive are GNN in their ability to express the number of graph polynomials, and with increasing degree. So as you might conjecture, GNNs are actually not that expressive. So for example, especially when the degree of the graph polynomials are high, not many of them can be expressed by the standard typical GNN architecture that I show you. Yes?
What is a graph polynomial?
So the graph polynomial, here I would not give you a complete definition, but it's, the idea is you will take the variable in the polynomials as your edges, and then you will try to, it can be defined on both simple graph and weighted graph, but basically you will take the sort of variable or the unknowns in the polynomial as the edges in your graph, and then the sort of the order of the polynomial can be loosely think about as counting some sort of motifs and subgraphs if the graph is taken as a simple graph. For a weighted graph, it's more intricate to explain it. So that's the invariant version of polynomial on graph. And then the equivariant version, the construction is a bit more complicated. But But if you're interested,
So, you know, so what is, for example, the graph of the one-point graph? I mean, tell us an example of that graph.
I see. So, for example, for a 1 point, there is so you can represent a graph as the adjacency matrix. So if this 1 point is basically like a zero matrix. So if it's just 1 point without any edges, then you get nothing.
Okay.
Yeah.
Like our loop?
Yeah. If you have a loop, then you have one variable.
It's just a linear.
Yeah,
And
exactly.
if you have two nodes connected by one arrow.
Yeah. I think in that case, if you have two nodes, you will have, I believe the variable you define is on the edges. So if you have two nodes and one edge, and let's say the edge is x1, 2, that will be your variable.
I see. So it has the same polynomial as the one with one node only.
But with a self-connection.
Yes, the one, yes. So those two have the same polynomial.
Oh, that's interesting. I need to check, and I'll get back to you on that. Yeah, good question. Yeah. But yeah, so this is more from sort of the perspective of invariant theory, where they're trying to use these equivariant functions on graph as a hierarchy to classify how expressive of GNN. So because recall that I give you one standard definition of the most popular GNN used in practice, but there are lots of different classes of GNN being proposed. So the idea is to use these kind of established functions on graph as a hierarchy, so that you can put your favorite GNN on this scale and see which one is more powerful than the other. And perhaps arguably, the most studied class of functions that people have used is this so-called Weissheimer-Lehmann hierarchy, or WL hierarchy. And this is a very popular heuristic that was developed to solve a graph isomorphism test. So what is graph isomorphism test? The idea is very simple. I'm going to give you two graphs. Let's say I give you these two graphs here. Can you find a sort of a bijection between them that map one graph to another? If you can find such bijection, then you conclude that these two graphs are isomorphic. If not, that they're not. So this is a notorious problem that has been studied quite extensively in theoretical computer science. It's not known that whether this can be solved in polynomial time yet, but it's conjectured. No, okay, let me not say conjecture, but it's shown empirically for the average case, you can solve this pretty efficiently, although the worst case might be very hard. So there are many heuristics that propose to solve this problem, and they've proven to be very successful, especially for average case scenario. And so one of these heuristics is this so-called WLL test that I'm gonna give you a more detailed walkthrough later on. But on a high level, how this WL test performs is it's going to do a graph coloring. So I give you two graphs. I'm going to give you sort of a iterative graph coloring algorithm. So at the convergence of the algorithm, it will output a multi-set of colors from these two graphs. So if these two multi-set of colors are the same, then the algorithm will conclude that these two graphs are isomorphic. Otherwise, they're not. So you can see that this algorithm are quite simple, but it has some limitation that it can't tell apart all the non-isomorphic graph pairs, but it's being used quite often in practice. But the sort of the connection that a few of these work have drawn in between the WL test and GNN is the idea of the algorithm nature. So recall a couple of slides ago, I showed you this picture of graph convolution, where I explained to you how in graph neural network, a node updates its own embedding by aggregating information from its neighbors. And so the idea or the design of this WL coloring algorithm is very similar, where how the color on each node is initialized as certain value and then constantly iteratively get updated by basically pulling the colors from its neighbor. and then apply a update via a hash function. I'll explain more details in the later slide, but you can see that there are some similarities shared of graph neural network and this WL algorithm. So lots of work had tried to sort of say how expressive of GNN are in terms of this lens of WL test. And in particular, it's proven in these two papers saying that the standard GNN, that the one that I showed you at the beginning of my definition, they have the same expressivity as the WL test. Meaning that if I give you a pair of graphs, the WL test will not be able to distinguish them, will classify them as the same graph, then GNN cannot distinguish them as well. But then here is an important footnote of these type of result. This type of result usually assume that the GNN takes in a constant input node feature. And because that's also sort of explain kind of the limitation of the WL test. A lot of times when people first run this WL test, they assume the graphs are not labeled or uncolored. So they start the test by assigning the same color of all the nodes in the graph and then update it. But of course, you can sort of like extend it of saying that I have some pre-color node and then I'm going to apply this test. But ultimately, let me explain it in another way, because I think I might confuse you a little bit here. So of course, you can apply GNN and WL test on inputs with non-constant features, for sure. But then a lot of the worst case scenario where this WL test failed is in the case where the graph are uncolored or have constant node features. So you can see that it's much harder to sort of, it's easier to fool the test if your two graphs don't have any node features, then all the information you have are the graph topology. So it's harder to do this sort of bijection matching. Yeah. So cool. So we have certain level of understanding of expressivity of GNN based on this WL test. But then one limitation of this test is the graph isomorphism problem is a binary problem. So it's gonna output yes or no, but it cannot capture the similarity across two different graphs. So then the question that we ask is, can we relax this binary graph isomorphism objective into something continuous? Can we answer that whether the network is able to capture the similarity and dissimilarity across graphs? So towards this question, there's been some recent works on sort of comparing GNN or connecting GNN with distances on graph. So I'm gonna quickly show you, due to the interest of time, in the next 5-ish minutes, some quick overview of results of what types of understanding that we can get by comparing GNN with graph distances. And these are joint work with my amazing collaborators. And we're going to answer specifically this type of question of, so can we map two similar GNNs, can we map two similar graphs into similar outputs by passing them through the graph neural networks? And also conversely, if now we observe the graph neural network always have very similar outputs for two graphs, can we conclude that these two graphs are similar in nature? And using some tools using some tools from sort of first extending this WL test to its continuous version and using tools from Graphon and Measures, we're able to show this equivalence as, sorry, my pointer stopped working. We're able to show this sort of main result as proving the equivalence of 4 objects. So let me try to, whoops, okay, sorry. So here we're showing this equivalences of the 4 different objects. The first 2 are sort of in the spirit of graph distances. So we have we've looked at various definitions of graph distances, and here I won't go into detail of defining it, but you can loosely think of, for example, the first one is to address the specific question that we asked here. So the idea is the following. I showed you earlier of this graph, of this WL test, and we can induce a graph distance from using the colors of the WL test, which I will give you some flavors in the next 2 slides. But then basically we use the WL test to allow us to define a metric or a graph distance. And then we say that if the 2 graphs are close in this graph distance, it's equivalently that they're also close in all their MPNN, in all their GNN outputs, with GNNs up to certain Lipschitz constraint and up to certain layer. So this, the equivalence of item 1 and item 3 precisely answer the questions that I asked here. And furthermore, we connected to the equivalence of 2 other objects. That the first is also this distance on graph, which is called tree distance. And this is defined in this earlier work by my co-author Jan Boka. And you can loosely think about this tree distance as, okay, I won't go into the details because you have to sort of look into the fractional isomorphism problem for graph and then define the distance from there. But then I guess a more intuitive connection of the tree distance is you can think of it connected to the homomorphism densities of trees on graph. So the homomorphism density is much easier to understand. It's basically to say that, well, I give you 2 graphs, and now can you say, identify what's the counts of like different kinds of trees as a motif in this graph. So the connection here we made is that if the homomorphism counts of all trees up to size k are close in this 2 graph, this also implies that their GNN output will be close, and which in turn have these equivalents with this tree distance and also this continuous version of the WL test that we extend here. Yeah. And so just to give you some quick flavor of how do we sort of relax this binary WL test into this continuous version, we're gonna go into that slide in 1 minute. But okay, if you care more about the sort of practical aspect, you might ask, okay, the theory looks nice, you prove equivalence of many things, but what can you make use of it? So in the graph distance community, a lot of the work have been devoted in trying to compute this distance more efficiently. So although lots of these graph distance can be computed polynomial time, but lots of them still it's like O to the n to the 5 order of computation complexity. So they're still quite slow. So a lot of interest has been on how to find efficient lower bound for computing the graph distance. So then, so there are like distance, say, for example, the like Gromov-Wasserstein distance on graph, like which are like very hard to compute. But even for the WL graph distance that we define here, which you can think of it as a relaxed version of the WL test, they still incur pretty high computation costs, which is polynomial time, but O(n) to the 5. And the reason behind, as I will explain our construction in the next 2 slides, will be sort of clear. But even in the graph distance that we prove the equivalence with in the main theorem, they are still not so efficient to compute. So the question that we asked, sort of inspired heuristically from our main result, is, so now we prove the equivalence if we can compute all the GNN output for all GNN up to certain Lipschitz constraint and layers. But now let's say we don't have all of them in practice, but we have enough number of them. Can we sort of use the output and their Euclidean distance of their output embedding as an efficient proxy to lower bound the graph distance. And then we provide some positive experiment result in the sense of if we were just to do some graph classification tasks, which here we're not explicitly trying to predict the graph distance, but you can loosely think of if you have a good graph classifier, that it most likely sort of know what are the relevant distance to look at so that it can classify the graphs well. So we compared the fully trained end-to-end GNN versus the GNN that we don't train all of its layers except the last layer. And then we found that if we use a sufficient sufficient hidden dimension in our GNN, even using this untrained GNN, they are quite competitive as their trained counterpart. So this can be loosely motivated in our main result, meaning that when we prove the equivalence of GNN output embedding and the graph distance, there is no sort of consideration of how the GNN are trained. So our main result just say if we have access to all the GNN and their embedding, we can show that they exactly capture the same thing. So now if we have enough number of them, even they're not trained, like their network weights are just randomly initialized and we're only training the output layer, they're actually still quite effective at sort of capturing or approximating the graph distance. And the effectiveness are demonstrated here by their sort of competitiveness in the graph classification task. So lastly, in order to convince you how this can be done, the basic ingredient, we have two ingredients. The first thing is we're now so how do we relax the binary objective to its continuous version? The idea is we're gonna turn a graph into a measure. So here we do not constrain ourselves to probability measure. We're just constraining ourselves to positive measure with total mass upper bounded by 1. And the idea is to sort of extract or induce this measure by running this WRL test, which I will now explain in more details here. So suppose I have a graph here. At the first iteration of the WRL test, I will initialize all the nodes with the same color. So here I assume I have an unlabeled graph. I don't have no feature. And so you can think of it as, so in a measure, you can think of now the support of my measure is just this constant color. And then I have the mass with, 1, which, the size of my graph. And I'm always going to normalize this mass to ensure my total measure is upper bounded by 1. And so now in my next iteration in my WRL algorithm, I'm going to do this color refinement. And so how I'm going to refine the color is based on basically my neighbor's color. So at each node, I'm going to say, take the set of my neighbor's color and also take into consideration of my own previous color. And then I'm going to sort of assign same value for all these tuples that share the same previous color and also their neighbor colors. So for example, in the first iteration is actually quite simple. In this case, it suffices to look at the node degree. So you can see that, for example, all the nodes with degree 2, meaning they have 2 neighbors, they all get mapped to the same color, yellow here, and then etc. So now if we think about it as a measure, how this sort of iterated measure now become is that we're gonna refine we're gonna sort of define, for example, for each of the new color, we're going to define its measure by having the support as the previous color and how many nodes are in the previous color. And then in the next iteration, we're going to then iteratively update. On the left-hand side, we'll be updating the graph again with some new colors. And on the right-hand side, when we define the probability measure, we're going to now change the support to the colors from the previous iteration and the number of the nodes with that color in the previous iteration. And so on a high level, we're going to do so by running this WR test and then iteratively sort of induce this measure from looking at the colors in the WR test. And by doing so, we're able to map this discrete object, a graph, into a measure. And now, how do we define the distance on the graph? Will be boils down to define a suitable distance on the measures. And so, yeah, but due to the interest of time, I'm gonna wrap up here. But basically, you can loosely think about the following. So I asked at the beginning, sort of the first quest is to understand how expressive are GNN to express functions on graph. And so we know that from this sort of very canonical graph isomorphism perspective, the most popular GNN that I defined at the beginning, they are no more powerful or they're equivalent in power as this WR test. And we can also show that it is also equivalent with the continuous version of WR test, which had connections to the related graph distances. So then, okay, that's the first part, and the sort of the underpinning principle of doing a lot of these is to explore this notion of permutation symmetry. But now, when we wanted to move on to answer our second question on how GNN generalize on different data, I'm going to sort of make a special assumption on my learning setup. And in particular, I'm going to invite you to rethink about whether enforcing this permutation symmetry is necessary. And so now let's take a look at how this permutation symmetry arises. So it arises from sort of the two fact of, it arises from this sort of the choice of node labeling that we pick when we arbitrarily wanted to, say, assign some ordering of the nodes in the graph. And in physics, this kind of symmetry can be loosely called as passive symmetry, because if you think about how the action of permutation works in this type of regime, you can think of, well, here I have a graph, and so I have a graph which I can think of it as a domain, and then I have some node features, so I can think of them as signals on the graph. So when I permute the node orders in the graph, I'm permuting both my node features and my graph domain together. And so loosely, you can think of this choice as a choice of the coordinate. And when I apply my permutation, I'm doing a change of coordinates. So in physics, sometimes they call this passive symmetry because the group action doesn't really change the object. It's just changing how it is represented. And this brings us back to think about the idea of the symmetry in convolution neural network, which is this very sort of canonical translation equivariance that's built in the design of CNN. But the interesting observation here is that if you think about, say, translation of small motifs in the images, the translation acts only on the signal while keeping the underlying image grid as fixed. So in physics, sometimes they call this kind of group action as active symmetry because it can also transform the object. So it's not just a change of coordinates. And so
sorry regarding that. If I can ask a question right now.
Yes.
Let's say about a Rubik's Cube or a puzzle. So they are like active symmetries when I am doing a move or moving some blocks.
Yeah.
Okay. Thanks.
Yes, I can hear you.
Yeah, that was the question. Like, is it an active or passive symmetry then?
Oh, so your question is, say, if I have a Rubik cube,
Yeah.
you can you can map like different pixels to different blocks, And your question is whether this is an active type of symmetry or passive type of symmetry.
Like, yeah, like if I am applying a move on the Rubik's Cube, like I am doing something permutation or something like that, so it would be an active symmetry or a passive symmetry?
In my view, I think that will be an active symmetry, because you're sort of, in some sense, can you loosely think of sort of the mapping as doing some sort of like a bijection on the same object, or you're doing some you're mapping one part, local part in this Rubik's Cube to another part of it. So I will view this more in line with the active symmetry.
Thank you very much. Yeah, then I
Yeah,
can.
so I guess maybe this can also be seen as this example on graph. So for example, the idea here that we're motivated is that in many graph learning setting, actually the active symmetries are more important or relevant. So for example, here, if we consider a human skeleton graph, and there are many sort of applications where you wanted to do, say, some pose estimation. So the idea is, if I have some input 2D coordinates of my joint, I want to reconstruct its original 3D coordinates. So you wanted to learn a map that maps the 2D joint input to the 3D joint input. But these joints are no features on your fixed human skeleton graph. And so here, the action, they only sort of really actively act on the no feature while keeping the graph as a domain as fixed. So here we argue that the active symmetries are more relevant, and maybe similar to the Rubik's Cube's idea here, when we think about the active symmetry on this graph, it's really its own automorphism, meaning that I can have a reflection symmetry of, say, the arms of the human skeleton, and I have another reflection symmetry of the limbs or the legs of the human skeleton. Right. So then basically in this work with my collaborator, we propose to, say, focus on these specific learning problem where the graph is fixed as a domain, and we want to learn functions that maps graph signal to some output graph signals. We argue that active symmetries are more important. So the conventional permutation symmetry, which is also known as the passive symmetry, they are important when you need to deal with, say, graphs without pre-matched order, because then you have an arbitrary choice of ordering. But then in these applications, the signals that's given to us, they're always aligned, or their orders are always matched. And hence we argue that by using the permutation symmetry, you can be enforcing too much constraint to your function class. And in the next few slides, I'm gonna make this claim more precise. So the idea is now, for this learning on a fixed graph setting, we effectively decouple the action. So if you recall previously, when I flashed the slide of permutation symmetry, my F will also take into the input adjacency matrix, as an input. But here, to deal with the cases of learning on a fixed graph, the input will only be the no signals, where we'll view the graph as fixed in the most basic setting. But of course, in the more advanced or in practice, you can still take the graph as input to break some symmetry. But let's consider the simple case. So for now, we're gonna decouple the action. So only let the action to act on the no signal while keeping the graph fixed. And so the way that we enforce this type of symmetry is to define a sort of another kind of graph neural networks, but they're very different from the convention, sort of the message passing type of graph neural network that I flashed out at the beginning. It is actually more similar to the sort of the standard neural network design. So you also have a bunch of layers. Each layer you have a linear layer and a pointwise nonlinearity. But the only key difference here is in the linear layer, we're gonna make this linear map equivariant with respect to the chosen active symmetry that I will define more concretely later. And you can think of it in the extreme setting, where, say, if I enforce no symmetry at all, this will recover the standard neural network. So now, okay, you might ask at this point, what are the sort of the natural active symmetry on the graph? And as I alluded earlier, one of the sort of the natural symmetry one can consider is the graph automorphism, which is the permutation that commute with the graph adjacency matrix. But then another sort of very important concern is in real world graphs and networks, they're typically very large. And so in large graph, it's very hard to find a global automorphism to precisely map one to another. But although they can exhibit some sort of local symmetries in the large graph. So how can we still enforce some non-trivial and useful inductive bias in these large asymmetric graphs? Because otherwise, automorphism will be a trivial, and we're basically just doing a vanilla neural network. So our proposal is we're going to define approximate symmetry via this notion called graph coarsening. So I'm going to give you a quick illustration here. So let's suppose I have this toy graph G with 6 nodes, and it only has this small local symmetry of flipping this node with this node. So how can I induce more symmetry to this graph G? So our proposal is first, we're going to cluster or coarsen this tree G into a graph G prime. So here I'm coarsening this left-hand side nodes into this coarsen node, and similarly for the right-hand side nodes. And then from this coarsen node G prime, I'm going to blow it up into a new graph with the same size as the original graph. But then when I blow up a coarsen node to a cluster with the original size of the cluster, I'm going to make this a fully connected graph or a clip. And so loosely, you can think of it by blowing up to a graph with the original size of this original graph G, but adding more edges. And so by doing so, we sort of introduce these local permutation symmetries. In addition, sometimes in this coarsen node G prime, we can have a global sort of symmetry because now this G prime is much smaller, so it's easier to find some global symmetry in this much smaller coarsen graph. And that's how we sort of induce more symmetry. And so we can turn a asymmetric large scale graph into still a graph with some approximate symmetry, because this is not the faithful symmetry inherent to the graph, but we basically modify the graph to be able to induce more symmetry. And lastly, with all these ingredients with the active symmetry and approximate symmetry, what I can show you is that we can have this discussion of a bias variance trade-off in selecting what is the right symmetry that we want to enforce. Because basically, I tell you that in this learning setting where learning on a fixed graph, I don't need to inherit to the permutation symmetry design. So then I have many different choices of symmetry and which one should I choose. So basically, we were able to sort of show like 2 results. So the first result is a simple lemma that kind of quantify the risk gap of any function versus its equivariant version. So I'm gonna take this function, project it to an equivariant space, where the equivariance is with respect to some chosen symmetry group GL. And so we can decompose this risk gap of the function versus its equivariant version into 2 terms, where the first term measures the mismatch of my chosen symmetry group versus the oracle but unseen true symmetry G here. So the first term is the symmetry mismatch. And then we have a second term that measures what's the constraint of the symmetry group GL induced on this function class. And from there, we're able to show a result, a precise trade-off of this bias variance in selecting the symmetry in a simple linear regression setting, where we also see sort of the bias induced from your chosen symmetry group. That's loosely, you can think about if I choose a large symmetry group, I might incur more bias because I impose more constraint of my function class. But then if I use too small of symmetry or no symmetry at all, I have too big of the function class, so that can introduce more variance. Right. So with that, we also have done a lot of, experiments on these learning on a fixed graph setting. In all these experiments, we can sort of see that crucially, if we use the original permutation symmetry, it will not give us the optimal performance. But whereas we relax the symmetry from some smaller symmetry group, it will give some performance gain. And in some sort of the task, we also sort of demonstrate this bias variance trade-off, where on this x-axis, it corresponds to the size of the symmetry group. So ranging from the largest symmetry group of the full permutation group to the trivial symmetry group. So with that, I'm going to conclude the last minute of this probabilistic symmetry, but this is sort of still like an ongoing research direction. So I don't have any results yet, but I'm happy to discuss if any of you are interested. I think in the last few years, many of you have seen that there is this rise in generative modeling, which is the goal is trying to generate new sample and to learn this unknown probability distribution, given some training samples from this distribution. And so in certain problem, because of the symmetry in this object, it's natural to assume that the probability distribution, the unknown target density, also satisfies some symmetry. Meaning that if now I apply a group action on this random variable, it will remain the same. Or the probability density of this random variable is remain invariant with respect to the group transformation. And so in the last few years, there are a lot of sort of the hype in using diffusion models. And basically it's one type of approach for you to learn this probability distribution. But then there is still a lot of sort of open question in this aspect. So for example, lots of the diffusion model now, when they apply it to do graph generation, say to model molecules or point cloud, they're based on this GNN backbones. But still it remains pretty open to understand, for example, what are the expressivity of these GNN-based diffusion model. Perhaps you would say that, oh, we already have some good understanding of expressivity of GNN, but those results are based on modeling or consider function class that are deterministic. But here in the sort of the generative modeling, you can think about we're trying to model stochastic functions, or equivalently, under some mild condition, you can think of it as learning some distribution. And here the distributions are maybe invariant or equivariant in certain way. It's not clear that whether you can directly, without any effort to extend the results, study and define for deterministic function to these probabilistic function or like learning distribution. So in my view, it's certainly very interesting and related, but still quite open. And then also up to now, I've always assumed that we have some known knowledge of the symmetry that we can start to work with, the permutation symmetry, or say the graph automorphism, etc. But in practice, when you deal with real data, you might not know what are the right symmetries. So how do we learn the symmetries from data? I think it's also quite an exciting future direction. So with that, I will conclude my talk, and thank you very much for your attention.
Are there any questions?
WL test, not a statistical test, does it just do one computation and outputs yes or no?
Yeah, it's a deterministic procedure. Yeah, but that's actually a very interesting question because there's been some work trying to enhance the power of this test. And the way that they do it is to feed stochastic input. So remember in this test, we have some input coloring, which are the initial assignment of the colors of the nodes. So they try to make it more powerful by say, I'm gonna assign random color at the initialization and run it multiple times. Yeah, so if you're interested, I can point you to some references of making a stochastic version of this test. Yeah.
Thank you.
If not, let's thank our speaker.